I'm super happy to be here. I'm Ekaterina, or shortly Katya, and I work as a senior data scientist at Nvidia, based in Dubai. And just to start, let me ask you, how many of you have been working in AI for over than 3 years? Raise your hands. Okay, some of you. So to all of you, I can tell you, I know how you feel. Well, at least that's... give me a second. At least that's how I feel for the past 2 years. While some of us are still tweaking parameters of convolutional neural network, the whole wave or tornado of new generative AI approaches sweeps out everything on its way and even making some jobs obsolete, right? But before I continue with talking about multimodal generative AI, let's take a look at the retrospective. For those of you who have joined us in the past 2 years, we used to have all these different architectures. We used to have convolutional neural network. Well, we still have them, right? But they were mostly used, convolutional neural networks were mostly used for tasks like image processing. GANs were predominantly used for image generation. RNNs, they existed for language and speech processing. And reinforcement learning was predominantly known in the context of robotics. The huge limitation of approaches like this was that, for example, to train a convolutional neural network, you would need a data set which would be labeled by human experts. And, well, for example, you need to solve a task of cat detection. You need thousands of cat images and bounding boxes around these cats, which human labelers would provide. So you can imagine that this approach is not sustainable, right? Because you cannot basically label the whole world of things if you want to develop something like artificial general intelligence. Then if you want to reuse this model and you want this model to detect dogs, for example, you still need to label it again and again and again. So it's not sustainable. And I believe we have found a sustainable solution, which is multimodal transformer architecture. So current transformer architectures, they've been trained on lots and lots of data. They consist of billions of parameters. And they've been trained in the unsupervised fashion on data from different sources and of different formats. It can be text, it can be images, code, sound, whatever. And these models, unlike their predecessors, which were discriminative, well, we call this old AI, discriminative AI, where we basically say, okay, we classify images, we detect objects in the images, we segment objects in the images. The new category of AI approach is called generative AI, meaning that we actually can create new content with these approaches. So, and this content can be also of different formats. It can be images, text, videos, 3D, code, you name it. So these approaches are already very much useful. In this approach, in this report called Sparks of Artificial General Intelligence, Microsoft, they were able to show that the GPT-4 model, GPT stands for Generative Pre-trained Transformer, and GPT-4 is the successor of the model known as ChatGPT. It's a multimodal architecture. So they were able to show that this model performs zero-shot tasks with accuracy of 82%. What do we understand by zero-shot? Basically, when we train a model, well, we have a foundation model trained on the whole scale of internet, and we don't specifically train this model to perform one or another task. So let's say we don't specifically train the model to detect cats in the images, but the model still possesses this ability to detect cats in the images. So we call it zero-shot. So imagine this model is able to perform zero-shot tasks with accuracy 82%. 82 is not a random number. It already indicates that this model is already very good and very useful. Another interesting example of how these models can solve challenging tasks. So in the past, I was working a lot in the industry called smart cities, where you basically use surveillance cameras or image-based recognition of some problems you have in the city. And one task is called visual pollution detection, where you try to detect different graffitis in the places they're not supposed to be. And those of you who have worked on similar tasks, you know that detecting a graffiti in an image is a very challenging task because graffitis can be different, they can be in different places, they can be like very tricky, like this one. So this one is kind of an interesting one with a 3D effect. But when you show this image of the graffiti to the new multimodal architecture GPT-4o and ask, is there a graffiti in the image? It's able to precisely say, okay, yes, there is a graffiti, and it's able to describe what's actually special about this graffiti. So it's a very hard task for convolutional neural network, but multimodal generative AI solves it very well. Another example is kind of scary. So you see here is CAPTCHA, and I did my PhD in computer vision before deep learning was a thing, and there was a very hard task for computer vision and image processing, and these models are able to detect CAPTCHA. To make you less worried, so this is ChatGPT, right? The OpenAI actually put guardrails in place. So if you go and test it with random CAPTCHA, it will probably won't work. It will say, okay, what are you trying to do is illegal. But somehow I managed to jailbreak it with this only example, and I was so excited when it worked. Another cool example is, multimodal generative AI is able to understand humor. So in this example, they have uploaded an image of the phone being charged by something which looks like an outdated VGA connector. And you all know that we don't charge phones with this thing. So the model has been able to precisely identify how many panels are in the image, what is there depicted in every panel, and it was also able to reason why is it actually funny. So AI understands humor. That's really exciting. In this demo, I'd like to show you how multimodal technology can be used beyond what we call image and computer vision. So here we show you how we connect in the agentic workflow. We connect a 3D avatar, a large language model, an automatic speech recognition model, and text-to-speech in order to enable gaming experience of the future where you, as a player, you go and interact with your game scenario, and it can develop based on, how you interact with it. So let's take a look.
We're thrilled to showcase an immersive and dynamic interaction between a player Kai and a non-playable character named Jin. This captivating ramen shop scene was created by Nvidia using the latest RTX rendering technologies. Nvidia collaborated with Convey, an Nvidia Inception partner, to showcase how developers will soon be able to use Nvidia Riva, Nemo, and Audio to Face for AI-powered speech, conversation, and animation. These models were integrated into the Convey Services platform and fed into Unreal Engine 5 and MetaHuman to bring Jin to life. Please take a look.
Hey, Jen. How are you?
Unfortunately, not so good.
How come?
I'm worried about the crime around here. It's gotten bad lately. My ramen shop got caught in the crossfire.
Can I help?
If you want to do something about this, I have heard rumors that the powerful crime lord Kuman Aoki is causing all sorts of chaos in the city. He may be the root of this violence.
I'll talk to him. Where can I find him?
I have heard he hangs out in the underground fight clubs on the city's east side. Try there.
Okay, I'll go.
Be careful, Kai.
I really love it. So this is how the gaming experience of the future will look like. And well, of course, it's been pre-recorded, but I can guarantee you we have this demo. It's running in our EBCs, and I've tested it. I usually ask this guy, what did he have for lunch? And he replies me that he had some ramen. So it's a fun experience. The technology behind is, as I said, multimodal generative AI, in this case for sound, but as I already mentioned, we can use it with different modalities. And usually how it works, we have a model, which is called foundation model, and as I mentioned, it consists of billions of parameters. That's why we need multiple GPUs to fit this model, and that's where Nvidia comes into play. These models, well, usually they can predict, once trained, they can predict the next series of tokens following the content provided to these models. And then, well, actually another popular architecture is also a mixture of experts. So we don't only rely on a single model, but use a so-called ensemble of smaller models, which is also a good architecture used these days. So once trained, we basically predict a sequence of tokens. And then we can take these tokens and we can fine-tune this model or instruction tune this model to adapt to different tasks. And these different tasks can be of different nature. So you can fine-tune the model to generate code. You can use these models to translate between different languages. You can use this for content summarization, be it summarization of text or image. You can show the image to this model and you can ask the model to describe what's going on. Or you can even pass a video and you can ask the model to describe what events are happening in this video. The models can be fine-tuned for image captioning, for sentiment analysis, also in different modalities, be it video or sound. Well, let's say you're in a call center and you want to know if your customer calling you is angry or happy. These models can be used for typical chatbot applications like question answering scenario, and for typical computer vision tasks like object detection, body pose recognition, and segmentation. You can also use foundation models and multimodal generative AI for that. This is one of the typical examples what you can ask a multimodal generative AI model to perform. So given an image, you can ask it to write an advertisement to sell this house. And at first it looks simple. So, well, we have an image and we want a model to describe what's there, right? But if you think deeper, it's actually more complex than that, because first of all, you give a model a task to describe. Yes, the model needs to understand what's in the image, but then the model also needs to write an advertisement. So you know that advertisements are usually written in a different language, using different words which address your emotions, right? And if you want to sell this house, so you need to show how beautiful this house is, or to highlight its specific properties. So you see that it's a multidimensional task, and it's all possible to do with modern technologies. Now, how does this work? So to train a model, so this is a very simplified architecture of our Villa model, which is a multimodal model for image and text understanding. And you basically train it to map images and text in the same embedding space. And in order to train it, you need millions of examples, millions of pairs of image and text. And now you might wonder, well, I mentioned that we train these models in unsupervised fashion, but now I'm telling you image and text. So, well, yes, it's sort of a supervised way, but you can actually get these labels in the so-called unsupervised fashion. So usually, for example, how OpenAI trained a similar model called CLIP, which I'll introduce a little bit later. They crawled 400 million of image pairs, image and text pairs from the internet, and they used the corresponding alt tag from the HTML to describe what's in the image. You all understand that it's probably not very clean, right? but 400 million pairs is a big number. So once trained, it's actually enough to provide good results. And in this scenario, you can also generate text descriptions. Imagine you already have one multimodal model, and you have more data sets, more images which are not annotated. You can use this model which you already have to create synthetic annotations of these images. And even further, you can use a large language model which you can prompt to take this coarse annotation and you can expand it into a fine annotation. I was trained this, it works quite well, and it helps you to improve your results dramatically. So in this scenario, you have an image and text, right? And well, we all know that images, they are just RGB numbers, and text, well, after you convert it into tokens, it's also numbers. But in the beginning, these numbers are different. So how do we take these numbers and we unify them in the same embedding space? In order to transform the image into the same token format as the text, we need to put it through the vision transformer. And this vision transformer, it can be a pre-trained transformer. It's basically, we do not train it in this approach, so it's frozen. We take this image transformer, and then we put another architecture on top. It's called projector. And the goal is to train this projector network to convert the vision transformer-based embeddings into the visual tokens. Then we take our visual tokens and our text tokens, and text tokens can be created by any tokenizer for text. So you then append these text tokens to visual tokens. Well, you concatenate them, and you pass this pair into the large language model. In this case, let's say Villa. So this Villa model, well, you still need to update the weights of this Villa model based on the pairs of images you show to it. And then in the outcome, what you would expect this model to provide is that when you pass an image to this model, you would expect this model to output this sequence of tokens which correspond to the text, and then you convert these tokens into corresponding text. Also, generative AI, multimodal generative AI, can be used to create images. And my own motivation was when I've discovered these applications which can generate your own portraits. I found it so fascinating. That's why I really wanted to learn. I really wanted to understand how this technology works. And I think I succeeded in this. So this was generated by the model I fine-tuned on my own images, not using any apps for that, and I'll tell you how it works. But before that, let's see what kind of use cases we can solve with multimodal generative AI for image generation. We can have two main categories of these approaches. The first one is unconditioned generation, where you basically don't have any text prompt, you have just a model which will create some random content it has been specifically trained for. Let's say a popular application like human face synthesis. This can be useful if you want to train a discriminative model for, let's say, face recognition, face detection, or you want to anonymize something. For that, you can just create some random faces. It can be also used for synthetic asset generation. A new, very popular application area these days is digital twin. You might have heard of that. Nvidia is also working hard on our Omniverse platform for digital twin creation. So in digital twin, you basically create a 2D or 3D representation of reality, and well, this 2D or 3D representation of reality needs to be populated by assets, and these assets are typically very expensive to create, especially in 3D. You need 3D artists, so why don't you just, if you want some like prompt, well, not very important assets, and you just want to populate your 3D world, why just don't generate them, right? Or these approaches can be also used to create super resolution images. So let's say you have a low quality image, you can apply diffusion, well, I say diffusion, but I'll introduce to you what diffusion means in a bit. So you can apply these techniques to create higher resolution images. And then, of course, we have condition generation, where you have some text prompt, and then you convert this text prompt into an image. So let's say you command your model to generate some specific object or subject. It can be also used for selective image editing or in painting. Let's say you have a photograph of you and your ex-boyfriend, and you no longer want him in the picture, right? So you can apply these techniques for that. And this can be also used for text, for text to image, and then text-guided image to image. Let's say you draw some very coarse sketch, and you want to convert this sketch into something very beautiful. You can also apply these techniques for that. A little bit of a history. So this all has started in 2018. And I remember it very well. I was attending the CVPR conference that year, and Nvidia has introduced the style gun approach. And I wasn't working at Nvidia back in the day, but I was so fascinating seeing like this paper which was showing how to use, well, guns back in the day to generate human faces. And they were so realistic. It was really, really fascinating. Then the next approach was Gauguin. It was designed to develop, to generate landscapes, very photorealistic again. And then, well, I remember somewhere 2 years ago when OpenAI has introduced DALL-E. This was so cool to see how you basically you were able to open a browser and enter a prompt, and then it would generate some image for you. I was really fascinated. But then approaches like Imagine by Google appeared. And then the approach Stable Diffusion has somewhat revolutionized the field because its creators, they have actually open sourced their model. They have open sourced the model architecture, which opened many doors to researchers all over the world who wanted to experiment with these models and with these architectures. And now we are witnessing development of the whole new families. We've seen models for image for text to video generation, for text to 3D generation. So it's very exciting. I promised you to tell you how this technology works. So here it is. And when we say text to image generation pipeline, we mean that it's not a single model, it's actually a pipeline of several models. And in the classical Stable Diffusion approach, we have 3 major components. The first one is CLIP, which is a multimodal model for text and image encoding. And then 2 other components are autoencoder or variational autoencoder and the unit component. So let me go through them one by one. Those of you who've been in data science long enough, you recognize this architecture as a popular architecture for image segmentation. So in the image segmentation scenario, we would have pairs of images and labels, which a human labeler would draw above them, and you would train your network to segment similar masks in the new images. The way it works, well, it's basically a 2-pass architecture, U-shape, as you see. We have a downscale pass and the upscale pass, and in all these passes, we try to extract the corresponding pieces of information. We also have skip connectors, which help to preserve information from earlier layers, and we pass it to the later layers. Turns out that this architecture also works well when we want to predict noise. And you wonder now, we actually want to create beautiful images, right? Why do we care about predicting noise? So turns out, if you predict noise iteratively, you can, at every step, you can predict it, you can subtract it from a very noisy image, and then step by step, you can arrive from a very noisy image to a clean and sharp-looking image. So in order to train it, we have our input image, and we also need to have a noise scheduler in place. So with this noise scheduler, we can modify we can tell our unit what is the amount of noise we want to generate, what is the distribution of noise we want to put there. So we use it then as a ground truth. And we use the same U-shape architecture in order to predict noise in the image. And then, of course, we compare the predicted noise and the noise coming from the scheduler, and based on that, we update the gradients of our model. These days, also, well, there are different architectures used, and somebody said, like, why don't we also use transformers for that? So another popular approach is to use the model called DIT, diffusion transformer, which is inspired by WIT, vision transformer. But, well, in my today's presentation, I'm focusing on units, but I thought it's important to mention that other approaches exist as well. So training unit works as follows. So you have many images, like millions of pairs of images and text. You pick an image, you generate some random noise using your noise scheduler, you predict this noise, and then you update the parameters of your model. Inference, unlike image segmentation, is also different. So in this case, we don't run inference only one time, but it's also an iterative process. So we start with the randomly generated noise, and at every iteration of our pipeline, we subtract this predicted noise from the image, and until we get nice and crisp image. This all would work well, but like, yeah, if you see that, well, we have images of large resolution, it might be computationally inefficient. So in order to compress your image, you can apply the autoencoder-based approach. Autoencoder is an architecture consisting of two models. We have an encoder, which basically takes your image and compresses it down into the so-called latent space. We then run all unit operations in the latent space. We run our predictions in the latent space. And then we use the second architecture called decoder in order to transform our latent prediction into the full-scale prediction. And you can imagine that training this is kind of straightforward, because what we have in the input, we also want to have it in the output. And this, what I told you before, would work for unconditioned generation. But if we want to have the full control on it, we need the large language model in place. And for that, well, Stable Diffusion used something like OpenAI's CLIP model. It has been trained on 400 million pairs of images and text, and basically it helps you to put your image and text in the same embedding space. It's a similar principle as I explained to you for Villa model, but here a little bit different that, well, first of all, when we convert our image and text into embeddings, of course they're different, right? But then we use the mechanism called contrastive loss function, where we basically compare our embeddings from image and embeddings from text using cosine similarity. And when they are very similar, then we encourage it by increasing by like giving the higher score. And when they are not similar, and we use negative examples for that, we penalize it by giving the low score. And then we update parameters based on that. Here, well, I show you how it all works when we put all pieces together. So we have our image converted into latent space from the autoencoder. We have our noise generated by our scheduler, and we have our text embeddings to control the prediction. We then also have in unit, we have the specialized cross-attention layers, which allow you to mix the text and image embeddings together, and we predict noise, which we gradually subtract from the image. This would also work for image to image. So here I'm showing you a sketch of a pink panther, and I draw it myself, so don't judge. I took this image. Well, you see, I'm not a professional artist, but I know generative AI, and with the help of Stable Diffusion model, I made it look nicer. And I basically prompted the model to generate me pink panther based on that. But then I thought, maybe I could turn it into anything, and I turned it into a cat. But then somebody saw this image, and they told me, Well, it actually looks like a bear, and I was able to generate a bear as well. But then, yeah, I saw, oh well, it might be also a monkey, a cow, and a pig. Had lots of fun doing this exercise. But coming back to the topic of portraits, I promised you to demystify how it works. So the technology behind is called Dream Booth, and well, one popular technology behind. And for that, you also need, again, many images. And you need a specialized input token. So here in this example, you see I put it there, a picture of OHWX panther. So this OHWX is this rare token which you use as an anchor to your model. So that's why you need to choose something which does not exist in the real world. Luckily, there are resources which help you actually to find what are the rare tokens are. Or as a rule of thumb, if you put something on Google and then open image search, if you're able to find many images to the token you've entered, then you shouldn't use this. So it should be something rare. So my name is Katya, and I was trying to use something like Katya, but in many languages, well, you know that, well, it may be decomposed in tokens like cat and something. So I was surprised to see the image generating lots of cats suddenly, until I realized it's not a good token. You need to use something rare. So you use this rare token, you put it into the context, and then you feed it through the text encoder. And then you also use an image sample, and you generate, you generate text embeddings. And then from the image sample, you generate a noisy image and a bit of a less noisy image. And your task now is to, well, predict, given a very noisy image, to predict a less noisy image. So you compare them, and you update the parameters of the initial unit model. It's also possible to do it in a different way. Instead of updating the weights of your unit model, you can actually update the weights of your text encoder, and this method is called textual inversion. You can actually use both of them. Did I skip that? Yeah, you can use both of them. Yeah, I wanted to show you my early experiments with this model using textual inversion. That was already more than 2 years ago, and you see it's not perfect, but my attempt was here to train a model which would incorporate the style of the Lion King and generate me pink panthers of that. You see that the subjects are not very perfect, but this style of Lion King is, I think it's there, so the model was capable into getting the style right, and it was already like one of the first stable diffusion models. I'm sure now it would be even better. But then, yeah, I mentioned the hybrid approach, so you can actually update parameters of both of the models, of the text encoder and your unit model, and it can lead also to more robust results. There is also another technique called low-rank adaptation, or LoRa. Well, applied to image processing, you basically take these LoRa layers, and it's a very simplified way to show you, but you kind of sandwich these LoRa layers in between of your original model without modifying the weights of your original model. So it makes it very lightweight. If you, for example, fine-tune your unit model and save checkpoints, they can be gigabytes. So I was quickly running out of space when I was experimenting with fine-tuning unit. But with LoRa's, you no longer have this problem because they are just a couple of megabytes. So it's nice, it works really well. Highly recommend it. You can also, affect the results of your generation by post-processing with prompts. So there are resources which actually have collections of artistic styles, because you know that these models have been trained on data from internet, and like many artistic styles are there already, so you can just try to get these artistic styles out through the prompts. Another interesting observation I've made is that actually punctuation in prompts really matters. So I've experimented with different setups. So this is like initial prompt which I used, a prompt and a negative prompt. And I tried doing both, removing all commas in the prompts and replacing them through brackets, and the results were very different. One other interesting observation is that prompts are biased, and so I was trying to generate a portrait, and the only difference in the prompt was I asked it to generate me New York in the background, and the person in the image was a Western-looking person. Once I've changed one and only word in the prompt, I asked for Chinatown in the background, and you see that the person has some Asian features. The same happened when I was using the artist with a Western name, and then I was using an artist style with an Asian name. And the effects were also surprising. Interestingly, you can also blend the prompts. The technique is called prompt blending, where you put some specific weights to one or another concept in your prompt. And by mixing, you can basically do mixing and matching here. And you can interpolate between one style or another. You can increase one style or another. So you can be very creative here. And this part, usually I enjoy doing a lot because it's very fun. There are also zero-shot approaches where you basically do not train your model, you don't fine-tune your model, but you use a sequence of models. So one model detects your face, another model should be pre-trained already to extract features from your face. So you extract embeddings from your face, and then you put them into LoRa, and you use this LoRa with your model. The downside here is that you cannot generate different facial expressions or different head poses. So usually like the pose in the image is still the same, but you can vary, different styles, and it's also very fun to work with. To finish my talk, I'd like to show you what Nvidia is doing in the field. So we have our Edify approach. And basically, Edify is a family of models. It all starts, of course, with static images, high resolution. We've trained it in collaboration with our partners, Getty Images, and the data set is, it's ethically sourced, it's free of bias, so it's a good one. We also have models for video generation, and I'm proud to tell you that I'm actually supporting the text-to-video effort of open sourcing this model. It will be available in our NEMO framework. And we also have models for text-to-3D. You can then export these models. And as I mentioned, you can populate digital twins like I'm showing you here. The possibilities here are really endless, and I'm excited to see what comes next.
Thanks a lot. It was very inspiring. And we have just the time for one question before our talk. So,
qui a une question en haut? Hop. Mais tu pourras pas traduire ça? En anglais? J'ai un très mauvais accent. Parle en français. I will ask my question in French and he will translate.
yeah, we can translate, no problem.
Thank you. Donc ma question c'est par rapport à la démo que vous avez fait au début dans le jeu vidéo. J'aimerais juste savoir c'est quoi votre avis sur au niveau hardware qui va être utilisé. Est-ce qu'il faudra plutôt faire des call API pour pouvoir communiquer avec une IA dans un jeu, ou il faudra que l'utilisateur ait ses propres ressources pour faire tourner le LLM? Anne-Claire, tu veux traduire?
Thank you. So in the demo you show before, what is your opinion about the kind of hardware that will be needed for the users that want to create this kind of gamer experience? Should it be like hardware they can access to? Should they have their own hardware? How do you see the ability for anyone to use this technology, I think, to create his own video game? I think more or less that was the question.
I mean, the question is like either create or use, right? And to create, you need an access to lots of GPUs because the data sets are big, the models are large. But then once trained, there are many ways to optimize this model And some of these models, they can fit a single GPU, and we also have the family of embedded devices like Orin. So I saw the efforts where my colleagues were putting models like Llama in a single Orin device, 70 billion parameter Llama. So this is possible, and like as gamers, most of the gamers who work with who play games with a lot of graphics, they already have GPUs. So this should be fine to use the same GPUs for these models as well.
Okay, thanks a lot. Thanks coming from Dubai.
Thank you.